Electrons are very important for understanding the properties of atoms. They impact things such as how reactive those elements are, which bonds they are likely to form, and many other properties. An important tool for helping us to understand the configuration of electrons in an atom are orbital diagrams. These help us know where electrons are in an element based on energy levels, sublevels, and orbitals. Let's talk about those terms first and how they relate to atoms. We know that the nucleus of an atom contains positively charged protons and neutral neutrons. Negatively charged electrons are found around the nucleus in what we often call orbitals, shells, or clouds. These are energy levels, and the further away an energy level is from the nucleus, the more energy it contains, or the more energy it takes to move an electron to this energy level. We're going to use an atom model with 4 energy levels. There can be more, but this is enough for most orbital diagrams. Each energy level can hold a certain number of electrons, and this is determined by the number of sublevels and orbitals on that energy level. Sublevels are described or denoted using the letters S, P, D, and F. Again, there can be more, but this is usually enough for most orbital diagrams. Each sublevel has a different energy, similar to each energy level. We also have different sublevels on each energy level. For example, the first energy level only contains the S sublevel. The second energy level contains the S and the P sublevels, while the third energy level contains the S, P, and D sublevels. Finally, the fourth energy level continues the S, P, D, and F sublevels. And this pattern would continue for additional energy levels and sublevels. Each sublevel contains a specific amount of energy, but these don't follow the strict pattern of energy levels as they increase. But these sublevel energies can be determined using this diagram. With diagonal lines, we can determine the energy of each sublevel from least energy to greatest energy. Here we are focusing on the first 4 energy levels and their sublevels, but we show additional sublevels and their energies in this diagram. Knowing the energy of each sublevel from least to greatest is very important because electrons will always fill the sublevel with the least amount of energy first. Here again, we are showing the energy in each level and sublevel from least to greatest. Each type of sublevel can hold a specific number of orbitals. We can think of an orbital as the path that an electron would follow around the nucleus. Each orbital can hold 2 electrons. Electrons can move clockwise or counterclockwise on each orbital, but they cannot go in the same direction. For example, all S sublevels can hold a total of 2 electrons, with each electron moving in an opposite direction, either clockwise, which we also call spin up, or counterclockwise, which we call spin down. P sublevels have 3 orbitals and can hold a maximum of 6 electrons. D sublevels hold 5 orbitals and hold a maximum of 10 electrons. F sublevels have 7 orbitals and hold 14 electrons. Again, each orbital can only hold 1 electron moving in each direction, spin up or clockwise, versus spin down or counterclockwise. Here is an example of an orbital diagram. The numbers represent the energy level. The letters represent the sublevel, and the dashes represent orbitals. The arrows represent electrons, with up-pointing arrows representing electrons moving in the clockwise direction, and downward-pointing arrows representing electrons with counterclockwise orbits. Let's review a few rules for drawing orbital diagrams. First, electrons must fill the lowest energy levels and sublevels first. Electrons like their space, so we must fill each orbital in a sublevel with an electron before we begin pairing them up. Electrons prefer to spin up or move clockwise in their orbits around a nucleus, so we must place an up arrow in each orbital in a sublevel before we begin pairing them up with downward facing arrows or arrows that have what we call spin down or counterclockwise orbits. The number of arrows or electrons in our orbital diagrams is based upon the type of element that we are representing. We find this information on our periodic table. Here we are representing orbital diagrams of neutral atoms. So the number of electrons is always equal to the number of protons that atom contains. We find this using the atomic number of that element on a periodic table. Let's take a look at an orbital diagram for oxygen. Notice that we fill the lowest energy levels first. We also fill each orbital in a sublevel with an up-pointing arrow before we begin to pair them up with a downward-facing arrow. Again, this is because electrons prefer their space in their orbitals and they prefer to spin up first. Here are a few more examples of orbital diagrams that follow our three rules.